Hello everybody, thank you for joining me in this session. Today I will explain a little bit about what I did for my project of applied aerodynamics course at the University of Illinois. So this session is titled The Development of a Self-Made Source Vortex Panel Method Code. My name is Dario Rodriguez and it's a pleasure to be here. Thank you. This is the outline that I will cover in this session. So at first, I will talk about what exactly the panel methods are and what is their purpose. Then I will summarize the methodology that I employ to implement this technique into a Python script. Afterwards, I'd like to show you some of the results that I got and how they are contrast with both more sophisticated codes like airfoils and experimental data available on the open domain. And finally, I would like to explain some of the conclusions and future work that is planned to be incorporated into this particular research. The panel methods are simply mathematical models that use potential flows to describe the behavior of an implicit flow field around an arbitrary geometry. So basically what we want to do is to model the flow field behavior around an arbitrary body geometry such as an airfoil. And we do this by combining a uniform flow, which is the free stream for our case, and potential flow elements. The most basic method is the source panel method, which employs a source sheet over the geometry surface of the airfoil, as you can see on the slide. And therefore, the problem is focused on determining the source strengths of each of those panels, which combined with the uniform flow will describe the physical behavior of the streamlines. The source strengths are placed in the midpoint of each panel, and these strengths are determined such that the normal component of the flow velocity is zero, because by definition the flow cannot go through a body, right? If it is true that the source panel method can help us to describe the flow field of symmetrical airfoils, since we don't use the circulation method, we are not able to calculate the lift. So to solve this issue, we need to add a circulation strength to the source panel method we previously described. And we then take advantage of the potential flows can be added to describe the flow behavior around airfoils, which are also subject to a certain angle of attack. Moreover, if we were to simply increase the angle of attack in the free stream and calculate the flow with a source sheet only, the rear stagnation point will not be located at the trailing edge. Instead, the flow will bend around the trailing edge, as you can see in the figure, and the stagnation point will be somewhere on the top surface of the airfoil, which is not a physical solution. This plot shows, for instance, how the streamlines behaves strangely at the trailing edge if we only use the source panel method, and make us realize that that the use of a source panel method is not enough, so we have to combine that with a Vortex panel method. In this way, I opt to develop a combination of both source, vortex, and uniform flows to describe the flow field around an airfoil. By placing a vortex flow, it is implicitly that I am going to set a Kuta condition also. So for this aim, as I said, 3 contributions are made. One is from the uniform flow, which belongs to the free stream velocity and also the angle of attack. And the second one is due to the source panels. And as I said before, each strength of these sources is considered to be constant within a certain panel, but it can vary from panel to panel. On the other hand, the vortex panels or the vortex strengths in the panels are set to be constant all around the airfoil. So that means that the strengths are constant from panel to panel also. So what about the methodology that I employed? So first of all, what I did is to import some of the coordinates of the airfoil that I want to simulate. And how I did this is basically using the beautiful sub-library from Python, which allow me to get documents from the internet through web scraping. And I used the website from the UIUC Applied Aerodynamics group to get the coordinates. This is, I think that I consider that this is a contribution to the work because it gives the user the opportunity to simulate airfoils that probably they don't have in their database, but probably they want to download and to optimize the code. Basically, what this part does is to avoid the user to go to the internet to download the document and then to process the document. So this part basically does all of that and saves kind of a little time to simulate. So what I did then is to define the panels and then discretize the geometry. So once I got the coordinates of the airfoil imported to the script, depending on what the user wants, he can choose how many panels he wants. And then according to that, a cosine distribution is created. As you can see in the red circle, which is in the figure below. And then the points are interpolated and placed on the airfoil surface. So the next step is to characterize the panels of the airfoil. So basically what I did is once I interpolate the coordinates according to the number of panels, I define it is important to define these two vectors for each panel. This right here represents the normal component and this one represents the tangential component. And this particular panel is a blow up of a panel located right here on the upper surface of this airfoil. So it is really important, this step, because depending on the location of the panel, these angles are going to change. Basically, these angles determine how the integral component of both the source and the vortex strands, how they change. So basically, this analysis is really important, but it is also quite straightforward because we can see in this plot that both beta and delta can be related through 90 degrees because they are separated by this 90 degrees angle and they are perpendicular to each other. So basically all the calculations are related to the beta angle right here. So basically in this plot what I did is to check if all the vectors, all the angles, in this case the beta angles, are calculated well, and I plotted the normal vectors in the midpoint of each panel, as you can see right here. So once we define the geometry of the panels, in this case what I did is to define the geometry as an object in the Python script. So it is really easy to manipulate the object with the attributes and the methods that were created for the panels. And this is really easy to make some modification for each panel also. So then what I did is to create this potential flow equation, which, as I said before, this flow field is described by the uniform flow, source sheet, and also a vortex sheet. And here are the equations of each one of their contributions. So getting inside in all of that equation that I presented, since we have to enforce that the normal velocity should be 0, we can get the normal velocity by deriving the flow field, by deriving with respect to the normal vector in this case. So once we derive this, we end up with this expression, which is only the source contribution to the normal velocity. And as you can see, this integral, it's kind of tricky, but it can be solved. And we end up with this expression right here. And this is really important because the derivatives, the partial derivatives that you can see over here, they are function of the angles right here. So these derivatives can be expressed as angles, and as the angle beta, and beta in this case is the angle from the positive x-axis to the normal vector in this case. So by convention, I applied that angle beta in all of my work. And also it is worth saying that since the data from the airfoils from the UIUC database are given in that order, in the counterclockwise order, I mean the first point is right here, and then the other point is right here, and the other point is right here in counterclockwise, right? So doing some math, I ended up with this expression right here, which basically is the same over here, but this is easy to code. So to solve this integral right here, it is worth saying also, note that these xg and yg expressions are dependent on s, and sg is function of basically or it is referring to the panel that we are analyzing, right? So sg is basically the direction that in which we need to integrate. So in this case, sg corresponds to this particular panel right here, and the direction of the integration is in this direction right here. So we ended up with this expression, and we have to solve this integral right here. And also note that since we are combining both source and vortex panel methods, the strength of the source panel of the source, they are function of each panel, so they can vary from panel to panel, which is different of what we got here for the vortex contribution to the normal velocity. So it's the same procedure right here. We end up with this expression, and also it's the same case. These partial derivatives right here can be expressed as a function of the angle between the positive x-axis and the normal vector to the corresponding panel. So also it is important to mention that in order to ensure that the flow leaves the airfoil in a smooth way, we have to ensure that the contact condition is fulfilled. In this case, to fulfill this contact condition through the modeling of what I am proposing right here, is that both the pressure coefficient of the first panel, which in this case is, the first one right here, should be equal to the pressure coefficient of the panel N, which in this case is not drawn right here, but it will be the panel right here. So those pressure coefficients should be equal. And since the normal velocities these panels also should be 0, the results of simplifying that is that we end up that the tangential velocity of the first panel should be equal to the opposite of the tangential velocity of the final panel. So basically that is the reason why these two velocities has different sign, or they are opposite to each other. So deriving this expression, in this case we get the tangential components by deriving the flow field, the field function with respect to the tangential vector, and we end up with this expression right here, and also the same case that we analyzed previously. We end up with this expression right here, and we can replace these partial derivatives as a function of the angle from the positive x-axis to the normal vector. So once we solve the expressions that I talked previously, we end up with a linear system of equations with n plus 1 rows and n plus y columns, and this forms the matrix A, which forms this linear system of equations where the unknowns are the source strengths and the vortex strength. And also to complete this linear systems, we have this parameter B, which is function only of the free stream velocity and the angle of attack. So this n plus 1 matrix is composed by 3 blocks. The first important block is that m by n is due to the source matrix. So this block of the matrix will allow us to compute the source strength right here, and the other block is the n by 1 vortex array to store the weight variable gamma in this case at each panel. It is constant, but it will affect two all panels as well, so it should be included to contribute to the normal velocity. And finally we got the array 1 by n plus 1, which is the condition, is the last equation that we have included in the code to get the matrix A and to get the unknowns sigma and gamma in this case, which represent the strengths. So after that, all that integration, all that operations carried out through linear algebra, we end up with knowing this column of unknowns, and then what we can calculate, or we are able to calculate, is the pressure coefficient, which is function of the velocity component, tangential velocity component on the airfoil surface. So we can calculate the pressure coefficient all around the airfoil because we have calculated the source and vortex strengths, so we are able to estimate these velocity components also. So then there's a measure of how the code is working, which is called the accuracy check. And basically what it establishes that the sum of the source strength times. So I have included this code snippet right here because I consider that this function is one of the most important in my code. So this is because in this function, what are the inputs are the control points of the panel that we are analyzing, and also the contribution of all of the rest panels, because this panel represents the whole contribution of the rest of panels. And this part is the direction of the integration where we are performing the calculations. Like I demonstrated before, these two values are going to change depending on if we are analyzing the integral contribution for sources or the integral contribution from Vortex. So basically this function calculates the integral of this function right here, depending on the direction that we will set. But this is kind of tricky because this can get in some mirrors, which I am still not sure, because this method basically uses a numerical integration and probably is prone to suffer oscillations when the number of panels are really small, or probably we find some singularities. So probably the implementation of this function should be optimized in the future. So once we determine all the parameters that I mentioned previously, we are able to calculate this pressure coefficient with this equation, because we have already calculated the tangential velocity, which depends on the strengths that we have already determined. So we are able to calculate this. And also, I have used this accuracy check parameter to basically check if the simulation is going well, and establishes that the sum of the individual source strength times the panel length should be 0 all around the airfoil. So this was only a way to monitor if the simulation is going well. And finally, here are the questions that I used to calculate the circulation of the airfoil, which is basically related to the circulations per length of each panel times the length of the panel. So this term is plugging in this equation right here, and I am able to calculate the lift coefficient through this equation. Here are some of the results that I got. These both plots belongs to the NACA 0012. Basically, since the airfoil is symmetrical, there's no difference between the upper and lower surfaces. But it is interesting to know that both amount of panels, this one with 30 and this one with 70, both agrees with X-ray results and also experimental data that I got from the NASA website. However, for the same airfoil, if we increase the angle of attack to 10 degrees, we get this difference between the pressure coefficients of the upper and the lower surface. And it's interesting also that the pressure coefficient right here is almost the same as the experimental data for this particular airfoil. And if we increase the number of panels, it is also interesting that the behavior right here, where the suction peak occurs, it is better modeled for this particular airfoil. So in this case, the increment of the number of panels is beneficial, and the calculated data resembles better to the experimental data. So this is the same airfoil, but in this case, the simulation was run for 15 degrees. These two plots represents the same airfoil. The only difference is that this is for 30 and this is for 70 panels. As the previous plots, once again occurs the same analysis, right? So increasing the number of panels allow us to better model and to get some nice results which aligns with experimental data and also with X-ray results. These last two plots shows the pressure coefficient distribution over NACA 2412, both for 52 panels, but this case, this plot is for an angle of attack of 0 degrees, and this right here is for an angle of attack of 8. So it is interesting to note that once we apply more cambered airfoils, or maybe more difficult or complex geometries, and the code is starting to diverge, so it is not um, capturing well the behavior of the implicit flow, at least here the leading edge and also at the trailing edge right here. And the same occurs over here in the leading edge once for the 8-degree case, and maybe here at the trailing edge. So that could be due to the integration method that I am using. So as I said before, that needs to be checked for future work. So also what I did is to compute the streamlines and also the pressure contours of the airfoil, because as we get the source strengths and also the vortex strengths, we are able to model the flow field by deriving the phi function, the flow field function by deriving with respect to x and to y, because we are able to but by this time we have already calculated both the strengths, so we are able to uh, calculate these contours, and it's interesting that the results aligns with what happens in the reality. We have an externalization point right here, and also a little stagnation point right here, which fulfills the condition. And also I plotted the same two plots for knockout 2412 and for an angle of attack of 8 degrees to check if the streamlines behave as expected, and it does. So what we can see here is that the streamlines go all around the airfoil and they end right here at the trailing edge, and they recombine right here. So they are fulfilling the Kuta condition right here, and also the pressure coefficient show us that there is a suction peak right here and also an externalization point right here. All of this pressure is negative, which produces basically lift, and the pressure right here is positive, which produces the combination of this pressure difference produces lift. So the results agree with what was expected right here. So no, okay. So finally, I'd like to show you briefly what I did in the code. So basically, I am using these libraries right here, and I created different modules to separate the functionalities of the code instead of getting all of the functions in just one script, which makes the code versatile also to a developer who is interested in modifying this. And then it's separated in auxiliary functions, objects, and plot functions with data and so on. So basically how the code works is the user gives an airfoil name, and if the code checks the database if the airfoil coordinates are stored in the database, and if not, then the code downloads automatically the coordinates from the UIUC database, and then starts the simulations once the code downloads the coordinates. And also here the user basically sets the number of panels that he wants to set for the particular airfoil, and then this function right here defines the panels. Basically what it does is to create all of the panels characteristics, like the length, like the beta angles and those kind of things, and it is saved in this object, the object panel. So I have implemented this object-oriented approach because I think that it is really versatile to work like that, because you don't have to manipulate all the variables within the code, and you only have to get to be aware of what objects you have Those objects usually have some characteristics associated to them, uh, and also some operations also associated to them, and those operations are saved within the object. So I have implemented that. Also, the free string is another object which is associated with a velocity and also with an angle of attack. And then these two parts are calculating the matrix to solve the linear system of equations. This matrix is due to the source strength, and this one is due to the vortex strength. Those are combined right here to form this bigger A matrix, and also the right hand side of that system of equation is calculated in this part. So basically what I'm doing here is to get the strengths, in this part, to get the strengths of both the source and the vortex strands. And finally, what I am doing here is to associate this gamma strand to compute the tangential velocity and to then calculate or to characterize the pressure coefficient and all of the rest of data. So basically, finally, what I'm doing here is to plot the free stream, the streamlines, and also the pressure contours. So this is what I did. Solutions that I got. So basically, the code works as expected, and it is able to estimate both the pressure coefficients and the distribution, the leak coefficient, and plot the streamlines and pressure contours. The results shows good agreement with the outcomes of more sophisticated software like airfoils and experimental results that I got from NASA. Part of the future work that I am planning to do is to refine the integration method. Probably I need to change the numerical integration approach that I am using right now to an analytical approach, because those integrals are can be solved analytically, so that could be better. And also probably I need to check how the increase of the number of panels are affecting within both the leading edge and the trailing edge, because those sections are sensitive to the change of the number of panels. Probably a cosine distribution would not be necessary once we reach a certain number of panels. And then what I want to do is to extend this methodology to a 3D complex body to check how it works, to describe the aerodynamic behavior of, for instance, a wing or a fuselage through these potential methods. And finally, I'd like to create a GUI interface to make the code more interactive, because probably if someone else who is interested in learning these kind of things probably will get confused once he gets involved, because there are some functions that cannot be understood at first instance. So that is my work. Here are some of the references that I used. I principally used this first reference, Fundamental of Aerodynamics of Anderson, and also this other reference, which basically it is a website which is focused on teaching aerodynamics through the employment of Python, which is really cool, because it will help you to better understand how the potential flow is manifested in reality through maybe to drawing some nice plots and those kind of things. I use this reference in particular to get the airfoil coordinates, and also these two ladder references to validate the code to get experimental data. So thank you so much for joining me, and I will be open to respond to any question.